When you see the padlock icon in your browser, it is easy to assume your data is protected by a single, impenetrable shield. We're going to deconstruct that assumption using this university cryptography exam as our roadmap. Look at question 8a, which asks about the Secure Socket Layer, or SSL, protocol. The protocol itself possesses no inherent mathematical security. SSL is an orchestration layer, a set of instructions that coordinates distinct underlying algorithms. To understand how this works, we will reverse engineer a secure web request. We will strip away the network protocol to look at the symmetric encryption doing the heavy lifting, and finally, the pure number theory that establishes trust in the first place. What we find is a strict dependency stack. If any single mathematical layer fails, the entire system collapses. Every secure session begins with the TLS handshake. This negotiation phase sets connection parameters before private data is transmitted. Before secrets are safely exchanged, the server must prove its identity to ensure the connection hasn't been intercepted. This brings us to question 1H on the exam, which tests the standard used for this proof of identity, the X509 certificate. An X509 certificate bundles the server's public key with a verifying signature. But notice what it specifically excludes, the symmetric session key. At this point, the client and server must agree on a shared symmetric key to encrypt the bulk of their web traffic, but they lack a secure way to send it. Any key transmitted now is vulnerable to interception on the open channel. To solve this routing problem, the network protocol hands over control to an entirely different discipline, asymmetric public key cryptography. The engine behind this secure exchange is the RSA algorithm. Look closely at question 5a, which provides the raw inputs, two prime numbers, p equals 3 and q equals 5, along with a public exponent. The first step in RSA establishes the modulus by multiplying these two prime numbers together to get n equals 15. In real-world implementation, this resulting number is massive and public. Deriving the original prime factors from that public number is the specific hardness problem securing the internet. To calculate the unseen private key, the system relies on a specific formula, Euler's totient function, referenced here in question 1e. The totient function counts how many integers are coprimed to a given number. For phi of 91, the answer happens to be 72. Applying this logic back to our RSA variables, we use a distinct shortcut. The totient of two multiplied primes is simply p minus 1 times q minus 1. For our exam variables, that means multiplying 2 by 4, giving us a hidden totient value of 8. This 8 is the linchpin to generate the private key, inaccessible without the original prime factors. For the final encryption step, using public key E equals 5 and message M equals 8, we take the message to the power of the public key, modulo n, 8 to the power of 5 mod 15. The resulting ciphertext can now be sent safely over the open web. The protocol has mathematically forced a secure key exchange between two parties without any prior trust. But this introduces a bottleneck. RSA prime factorization is computationally exhausting. If a server attempted to use RSA to encrypt a 4K video stream, the processing load would crash the hardware, so the architecture shifts. Once RSA safely transfers the secret session key, the SSL protocol immediately abandons asymmetric math. It switches execution over to symmetric block ciphers. Question 1c highlights the mechanics of this shift by referencing a legacy symmetric cipher, DES, noting its 16 rounds of operation. A round replaces the elegant prime math of RSA with brute force structural complexity. The algorithm divides the data into a grid and repeatedly scrambles, substitutes, and shifts the rows using subkeys. Today, we use the Advanced Encryption Standard, or AES. Look at question 1D, which details AES using a 128-bit key, 10 rounds, and 176 bytes. AES achieves its security by expanding a single 16-byte key into 176 total bytes of key material. It uses this expanded material to uniquely scramble the payload at every one of its 10 distinct rounds. Symmetric ciphers trade mathematical elegance for raw operational speed. They rely on structured confusion and diffusion to process gigabytes of web traffic seamlessly. Let's look at the assembled system. SSL orchestrates the connection at the top layer, RSA is the key, and AES encrypts the data. But to guarantee an attacker hasn't maliciously altered those packets in transit, we need data integrity. The solution is found in question 1J, which defines a digital signature as encrypting the hash of the message with the sender's private key. This is a reverse application of asymmetric math. Instead of encrypting data with a public key to keep it a secret, we encrypt a mathematical summary, a hash, with a private key to prove authorship. Question 7b identifies the ultimate goal of this process, non-repudiation. Because only the sender possesses their private key, a valid signature irrefutably proves they are the entity who sent the data. The security of a web request is the result of a precise sequence of handoffs between these distinct cryptographic disciplines. Trust is established by number theory, speed is delivered by block ciphers, and integrity by cryptographic hashing.